Hello, welcome to Not for Exam, and I am your host Sujit, and we are going to discuss phase change on reflection and refraction. When an incident EM wave or light wave reflected from a mirror etc. at point of incidence, phase changes by pi. That means phase difference between incident wave and reflected wave delta phi will be equal to pi. And when an incident EM wave or light wave refracted from one medium to other medium, then at point of incidence both waves are in phase. And when an EM wave or a light wave is reflected at the interface of two medium having refractive index μ1 and μ2 respectively, and if wave is reflected from the surface of a optically denser medium, that is μ2 greater than μ1, then at point of incidence phase changes by pi. And if wave is reflected from the surface of an optically rarer medium, that is μ2 less than μ1, then at point of incidence phase difference between incident and reflected wave is 0. Thanks for watching Not for Exam, and we will see you next time. Hello, welcome to Not for Exam, and I am your host Sujit, and we are going to talk about Lloyd's mirror experiment to observe interference. In this setup, image of a source by a mirror is used as a coherent source. As in the given figure, image of a source S and its image S dash by the mirror behave as two coherent sources of light, and interference pattern is observed on the screen where light from both sources S and S dash is present. Geometry of sources and screen is similar to that in YDSC, and for d very less than d and theta tending to 0. At p, path difference will be d theta, that is dy by d, and phase difference due to path difference will be 2 pi by lambda into dy by d, and phase difference due to reflection is pi. Therefore net phase difference delta phi will be equal to 2 pi by lambda into dy by d plus minus pi. Here we can take plus pi or minus pi. For maxima, delta phi will be equal to 2n pi, and for minima, delta phi will be equal to 2n plus 1 pi, where n is equal to 0, 1, 2, 3 and so on. Thanks for watching Not for Exam, and we will see you next time. Hello, welcome to Not for Exam, and I am your host Sujit, and we are going to talk about a typical setup of Fresnel biprism. In this setup, two images of a source formed by the biprism act as two coherent sources of light. Fresnel's biprism composed of two very thin prism of very small prism angle. As shown in the figure, S1 and S2 are two images of the sources by the two halves of the biprism. Geometry of this setup is same as a typical YDSC, and therefore fringe width will be lambda d upon d, where d is equal to a plus b and d is equal to S1 S2. We can find d in terms of a and prism angle alpha. For very small prism angle alpha tending to 0 and a very greater than d, by geometry d by 2 is equal to a delta, that is a mu minus 1 into alpha. Since for very small prism angle deviation is same as minimum deviation, and d is equal to 2a delta, that is equal to 2a mu minus 1 into alpha. Now fringe width beta will be equal to lambda d by d, that is lambda a plus b upon d, that is lambda a upon d 1 plus b upon a, that is lambda upon 2 delta 1 plus b upon a. Also if a very greater than b, then beta will be equal to lambda upon 2 delta, that is equal to lambda upon 2 mu minus 1 into alpha, and we can say that beta is independent of a and b for a very greater than b. Thanks for watching Not for Exam, and we will see you next time. Hello, welcome to Not for Exam, and I am your host Sujit, and we are going to talk about shape of interference fringes in typical Young's interference experiments. If the sources are in the form of long slits, which can be assumed as lines of array of point sources, then in the central portion of the screen fringes are straight having equal spacing, and as in the Young's double hole experiment, if there are point sources, then same order of fringes obtained where path difference delta x, which is S2p difference S1p, will be constant, and by the property of hyperbola, locus of point p will be hyperbola. Therefore hyperbolic fringes are obtained on the screen. Thanks for watching Not for Exam, and we will see you next time. Hello, welcome to Not for Exam, and I am your host Sujit, and we are going to discuss shape of interference fringes by 2 point sources in different planes. Locus of point P for which path difference from source S1 and S2, that is S2P minus S1P, is constant, gives the location of particular order of interference. By geometry, the locus of point P is hyperboloid in 3D space as shown in figure 1, and shape of interference fringes in a plane is the intersection of hyperboloid with that plane. Figure 2 shows a plane with circular intersection with hyperboloid, therefore in this plane circular fringes are obtained. Figure 3 shows a plane with hyperbolic intersection with hyperboloid, therefore in this plane hyperbolic fringes are obtained. We are going to discuss interference in thin films. Let's take a look at the gain figure of a thin film for normal incidence and oblique incidence. Reflected waves after first and second reflection are wave 1 and wave 2 respectively, and transmitted waves after first transmission and second transmission are wave 3 and wave 4 respectively. Now optical path length difference between wave 1 and wave 2 is twice mu t, and phase difference between wave 1 and wave 2 caused by reflection will be pi. Therefore for constructive interference in reflected wave, that is for a strong reflection, twice mu t will be equal to 2n plus 1 into lambda by 2, and optical path length difference between wave 3 and wave 4 is twice mu t, and there will be no phase difference caused by reflection in wave 4. Since reflection is from denser to rarer medium, therefore net phase difference is only due to optical path length difference. Therefore for constructive interference in transmitted wave, that is for a strong transmission, twice mu t will be equal to n lambda. And for weak transmission, that is destructive interference in transmission, twice mu t will be equal to 2n plus 1 into lambda by 2, which belongs to strong reflection. This is due to energy conservation, that weak transmission belongs to strong reflection. Also, if film thickness is much less than lambda, in that case twice mu t will be very less than lambda, and therefore phase difference due to optical path length difference is almost 0, and therefore net phase difference is pi due to reflection and is equivalent to lambda by 2 path length difference. In that case, there will be destructive interference in reflection. So very thin films appears black in reflection. We are going to talk about thin film interference of a coating on a glass lens. As shown in the figure, on a glass lens of refractive index mu g, there is a coating of a material of thickness t having refractive index mu c. If mu g greater than mu c, then for both reflection, first from air to coating where mu c greater than mu air, and second from coating to glass where mu g greater than mu c, phase shifts due to reflection are pi or equivalent to 0.5 wavelength in both reflections. So only the optical path length difference twice mu c t, that is for normal incidence, determine the net phase difference. Therefore, to eliminate wavelength lambda naught in reflection, minimum thickness t naught of the film required is given by twice mu c t naught is equal to lambda naught by 2, or t naught is equal to lambda naught upon 4 mu c. We are going to talk about Michelson interferometer. As shown in the figure, monochromatic light beam from source S incident on a semi-transparent mirror M, which acts as beam splitter. Transmitted beam reflected from fixed mirror M1 and reflected beam is reflected from movable mirror M2. The above two reflected beam recombine at the beam splitter, and the two recombined beams are directed towards the detector D, which measures the intensity of the interference pattern. Also, optical path length difference between wave 1 and wave 2 will be twice d2 minus d1, where d1 and d2 are arm lengths for mirror M1 and mirror M2. It can be seen that shifting mirror M2 by lambda by 2 distance, that is changing the length d2 of arm 2 by lambda by 2, changes the optical path length difference by lambda, thus shifting one fringe in the pattern. Also, we can understand that inserting a thin transparent sheet of refractive index mu and thickness t will change the optical path length difference between wave 1 and wave 2 by twice mu minus 1 into t, and therefore the number of fringes shifted in this case will be twice mu minus 1 into t upon lambda. Thanks for watching Not for Exam, and we will see you next time.